Okay, so this is the last of the current series of lectures on the algebraic theory of surgery, and I want to explain the relationship between the chain complex theory and the real theory. So this, so the real theory, topologically, is going to be spaces X, spherical fibrations, one, two, three, Poincare duality spaces, the Spivak normal fibration. So here I'll just be dealing with a space with a spherical fibration, whereas here the Poincare duality would determine the normal fibration. So this means that F is a degree 1 map, and B so not only do you have a map of spaces, but you also have a map of circulations. I missed out one. I have to think with that. 2 prime. I really want to have 3. So I'm sorry, I should mess this up a bit. 3 will be X nu rho. Well, this is a normal space. So it says quid. And the Poincare duality would have so there are 5 now objects in topology, and all have algebraic images. So this is the topological side, and on the algebraic side are chain complexes with extra structure. And it will always be the case that for each of these 5 types of things, there will be an algebraic image. And the most important one of these is 5, because that's where you have something which determines the surgery of structure. But kind of to understand how to pass from this normal map to a chain complex vector structure, you have to kind of go through the first part. So 1 is symmetric complexes. Symmetric chain complexes. So that's C, that's a chain complex. And the extra structure is an element of this. I won't worry too much about the grounding, that I'll just take Z. And I want to remind you what W is. We did this last time. So these are the symmetric Q groups. 2 was spherical fibrations. So this is going to be hyperquadratic chain complexes. So this group is kind of looks like this, using the complete Tate So remember, this is covariant in C, but this is contravariant in C. So this passage from spherical fibrations to hyperquadratic complexes is contravariant. It's a bit like K-theory. So let's call the chain bundle. So just as topological K-theory is contravariant in X, so this algebraic theory is contravariant in C. And it's a non-trivial but interesting theorem of my devices that this is really just H, how shall we say it, from this whole group is like that. So it's like the crucial thing here is the Wu classes. So it's slightly confusing because there are Wu classes here and here. These Wu classes here look like this. Let's just take the even ones. I should probably tell you what the subscripts mean here. But the point here is that these are basically, let's call them VR phi. These correspond to such a space has spin node squares. I won't have to explain where these Wu classes come from directly, but they come, it's actually spin node squares in cohomology. Now, maybe I should basically have some. Z2. Okay, so it's basically the dual over here. Slightly peculiar dimension shifts. Now, Poincare duality space, it's not immediately obvious. So normal spaces, I missed that one. It's normal space. So normal space is when you have not only a space, a fundamental class, and a spherical vibration, but also this curious degree 1 map. So that's where the Kurevich is a spherical Tom class, as it's called. And it means that not only is this homology class, the fundamental class, that is represented by a sphere, but not in the homotopy of X, but in the homotopy of the Tom space. So it's very unusual if you take a homology of a space for it to be spherical. But in this context of surgery theory, one looks quite often at what one could call algebraic normal complex. So that consists of a chain complex, a symmetric structure, and extra structure is that you've got a relationship between the spherical fibration and the homology class. So one needs, for various reasons, to understand how this relationship plays out in algebra. Okay, so the symmetric structure is easy. We just take a symmetric construction on X, then there's some kind of co-symmetric on the Tom space. But this is slightly more complicated. So what you've got are Q and C. Then there is this that. So there are two things. There's a symmetric structure coming from the evaluation of the fundamental class. And you've got a chain bundle over here, and there's a map from here to here given by phi naught. So phi naught is a chain map. Every time you have a symmetric structure, you have these chain maps. Well, just do this. And you can push forward, because it's a map from the cochains to chains, the chain bundle structure to not a symmetric thing, but a stable symmetric thing. And what the chi here is doing is simply saying that on the chain level, let's call this, so the chi is quite a subtle thing, because it's not a cycle, it's a chain. It's a chain which measures to what extent the Wu classes of X, as defined over there, are the Wu classes of gamma. And in this situation, where you have a space which has both a spherical fibration and a spherical tone class, there is a connection, namely that it's the formula of Wu and Tom. So if you've got a space with a spherical fibration and a spherical tone class, and the homology, the fundamental class, is the image under the Thom isomorphism of that, then there's a connection between the Wu classes of X, as defined here, and the Wu classes of nu, as defined, well, similarly. But so that's quite an important thing, that this is the algebraic version of the fact that the Thom space is S dual to X itself. Except it's not quite S dual, because you don't have Poincare duality. But it's an expression in this context. There is a close connection between the S dual, do this a bit more slowly. What in a situation where, so this is just an abstract definition. Algebraic normal complex has 4 components: a chain complex, a symmetric structure, a chain bundle, and this clutching chain relating the stable symmetric or hyperquadratic structure determined by phi, J is somewhat undefined at the moment, and the push forward of the chain bundle. But it is just an algebraic version of a standard formula of Wu and Thom relating the Wu classes of this pivot normal fibration to the Wu classes of the underlying space. And it comes because you have a fundamental class which is spherical in the sense of Thom. So it's quite complicated, but it's not impossible, because I'm just taking standard, well, what I hope should be standard objects, and saying, well, let's go from the topology to the algebra. I might perhaps remind you, I think I already did this last time, what J is. Oops. It might be a bit clearer. But before I do that, let me so this is now 3. 4 is just saying that the only difference between 3 and 4 is that I'll now say that if I have a Poincare duality space, gamma and chi are determined by the Poincare duality. So every Spivak normal space has this Spivak normal structure, right? Nu and rho. And similarly here, every symmetric Poincare complex has these for free, so to speak. Now, that's the beginning of it. The end of it will be part 5. We have a normal map. So in a situation where part of all of the normal fibration is trivial, such as for framed manifold or a framed Poincare duality space, there's a quadratic structure. So that's kind of, let me remind you what J is. So that's a typical cycle in this space, the chain space, this chain complex over there. So you have, and the phi s lives in here, so phi naught, for example, would be that, would mean exactly that phi naught is a chain map. Because C tensor C Well, I'm assuming that C is finitely generated free Z model. That's because in the applications, X would be a finite CW complex. So the Seda chain complex looks like that. Okay, so what J looks exactly the same. Except because I'm using the complete resolution, this Q hat, I have to tell you what J is in negative dimensions. And it's 0. And this is the exact analog of cap products vanish in suspensions. We don't talk much about it. But this is like forcing that to happen. So algebraic cap products vanish in suspensions. Now, what keeps things together is an exact sequence. Looks like. So, if you have a space which has, I'm going to skip forward, we'll just go on to 5. If you have a normal map, part of M is X, and the rest of M is where the bundle is trivial. Okay, so, and we're going to use the explaining the algebraic translation of a bundle map, what is the crucial, how do you see the choice of B in algebra? So, a framing, a part of mu, which is trivial, or the part, corresponds to the kernel of J. If you look at this equation, this says that the J, the image under J of phi, is equal to exactly that gamma. So this is the exact part of the symmetric structure of such an algebraic normal complex, which is determined by the normal fibration. Slightly complicated, maybe I should do this a bit more slowly. So, corresponding to 3, having exactly 3, a normal space, I have 3 components, a space, a spherical fibration, a spherical Thom class. Here I have a translation into a chain complex, a symmetric structure, which depends only on the fundamental class, on the image here of the Thom space, of the, so the spherical Thom class. And I have a chain bundle and this clutching map. What's going to happen now is I'm going to say in a normal space, I have the symmetric structure. When I move it by J, this depends on the normal. So wherever the normal fibration is 0, I have something in the kernel of J. And better still, whenever I have a reason, as I have here, why part of this normal bundle is trivial, that means that I've got something in the long exact sequence. So let me just go forward a little bit. So, fundamental exact sequence, algebraic exact sequence, for quadratic equals J is 0 with reason. Reason is crucial here. So this is just an exact sequence which looks like this. Okay, so we have for any chain complex C, there is a long exact sequence which tells me that symmetric, hyperquadratic, a symmetric structure has J0 precisely when it comes to a quadratic structure. And this exactly is it's the long exact, and this is quadratic here. Looks like this. So there's a short exact sequence. Maybe I should put this slightly wrong. Not very wrong. Well, very wrong, but not seriously. Looks like that. So there's a dimension of 1. So this short exact sequence still wrong. Short exact sequence of ZZ of free so W is the standard free resolution of Z as a Z2 module. W hat is the complete resolution, and I'll draw a picture. And this short exact sequence determines this long exact sequence, as I'll explain in a moment. And from this, so this is the J here. It's going backwards, because this the undefined term is so this is the thing which says takes a symmetric structure, a stable symmetric structure, and if some symmetric structure is stably 0 homologically, that's why you need the chi, the choice of chi tells me there is a quadratic structure, which the symmetric structure is quadratic. So the difference between quadratic and symmetric comes up very naturally on this level, both on reasons of this short exact sequence, which I'll back up more carefully, and because this is exactly how if you have a normal map on the part of M which doesn't come from X, you get a quadratic structure, which is the Serge-Rho structure. So the whole aim of this is to have an algebraic theory out of which comes out the quadratic Serge-Rho structure without doing any Serge below the dimension. So Wald's great theory used the Browder's normal maps and a mental group and so on. And the real problem with Wald's theory from the point of view of kind of further development was how to avoid having to do surgery below the middle dimension. Okay, so let me fill in some of the details, and then I'll go to the search abstraction theory. So, particularly I want to explain what 1 plus t is. So Q lower NC is collections like this. It looks very similar to the symmetric things I just erased. But I want them both here. Okay, now, what is 1 plus t? 1 plus t of a quadratic structure the quadratic, remember that this is J. The hyperquadratic things are determined by the Wu classes of phi. We know the Wu classes of phi are the same as the Wu classes of the algebraic chain boundary. So this is the key point at which you see that if you have a symmetric structure, which is stably zero in the sense here, that's the equivalent as the Wu classes being zero, and a particular reason having the Wu classes zero means there's a quadratic refinement. So quadratic things are, a chain complex has a quadratic structure when its Wu classes, remind you what the Wu classes are. Like that. So it's fairly obvious that if you have a, what's certainly true is that if you take a look at the composite, that that's zero. Because these things are zero here, so that's not the problem. The problem is to make sure that one has a reason, that's what all this homological algebra, this short exact sequence, using the long exact sequence, is that if this is an element here goes to zero here, then it comes from a quadratic structure. And this kind of sense. So this was a kind of breakthrough for me at least, to understand where do quadratic structures come on chain complexes. They come exactly when a symmetric structure is stably zero. And, well, one has to kind of see what this has to do with normal maps and so on, but I mean, this is really quite a useful thing. So this is like saying, just mind you, this is like h minus n. These are the orbit spaces of the Z2 action. These are the fixed points. And these are the take homology. So this is a nice exact sequence which goes back to Platon and Allenberg. What of course they didn't know, should they, is the connection is geometric topology and normal bundles and normal vibrations and normal maps and all this stuff. Okay, but this is the, maybe I can do a simple example. Let me take the very simplest example of this without any. Let's look at a space which is highly connected. Okay, so that's actual space. Let me. So here I'm going to have 1, 2, 3, 4, 5, 6. Okay, there's always a degree 1 map. That's not surprising. Oriented, of course. Okay, so I mean that's F. You can just do standard, the theorem of Hobbes. It is, and I mean, just do it. It's well known that this is such a thing. There exists. Okay, there are not that many vibrations over sphere, so this is going to be taken to be trivial one. Sphere, I mean, it's well like the very beginning of we just take the sphere configuration to be the trivial one. If and only if the normal bundle, I'll call it SO, is stable, or stable normal bundle. It's not just trivial, because B is the same so this is over X and this is over M. So in this case, the bundle map, which is such a standard feature of surgery theory, is exactly realization or fiber homotopy realization of so what's going on here? In this example, I'll relate the choice of framing, we'll assume of M, so this only works if the N is actually stable trivial, and in fact the VU classes are the primary obstructions to the existence of such a framing. But if M is fiber homotopy trivialized, the normal bundle of M, then corresponds to
this is a different J. This is J in this sequence of
yes,
classifying spaces.
you're quite right. There actually is a connection between the two J's, so it's not immediately obvious. So this is the J homomorphism of, well, I think that, well, I think it's the other Whitehead, GW Whitehead, is the first person. Okay, corresponds to a choice, to a quadratic structure. Psi on phi so let me look explicitly at what is the symmetric structure on the chain forms of M. So M in this case was M assumed carefully was K minus 1 connected. All that really matters is the top and bottom. And top and bottom are very simple, and the middle is not particularly simple. So in our case, I should say example, because it's a good word at this point. So Cm Cx so we have the standard thing here. So I didn't mention it this time, but I did mention it at the very end of the last lecture. There's such thing as an Umkehrmap. And in this case, all that you've got is this thing here in dimension k. Now, let's go. So our chain complex, where we're going to look at symmetric and quadratic structures, is given by this. So these are where T so these are the minus K symmetric forms so the symmetric structure is the form the standard one. Because that's just the cup product pairing. So the symmetric part, or the symmetric complex in this situation, is just the module, the finally generated free module, free, of course, because I've made a serious assumption here, together with this minus K symmetric form given by evaluation. So under what circumstances does there exist a quadratic refinement? Also, what is a quadratic refinement? Well, topologically it's this. Algebraically, let's look at the exact sequence. J, this these are the fixed points. But there is this minus the K factor. This is X tends to Y. And this is the, we have to have, of course, sign conventions, and they give you the exact right thing. So, in terms of this E here, it's 1 plus. So you can see why this is Z2 torsion, by the way. Z exponent Z2. So you get a symmetric matrix, or symmetric form here. This part, we only look at the diagonal terms. So phi goes to the diagonal terms of phi. And that's what the Wu classes are. This is almost a linear map. To write properly. So the crucial thing here is that having a reason why this is close to 0 in here is the same as being able to express phi like this. So we know that phi, T phi, so we know that for free, so to speak. The question is this minus to the k symmetric form here actually of this type? Does it have a quadratic refinement? So the quadratic refinement exists if and only if these group classes are 0. In the case when k is even, that's enough, because this is injective. If k is even, with image, the even symmetric forms. Point being here that as the form is even, if this integer the self-intersection homologically is always even. So there's no terrific advantage to looking at this group when k is even, because it just says that the diagonal lengths are of type 2. Okay, so the key idea is that if you have a fiber homotopy realization of a 4-dimensional manifold, say, then the intersection form, diagonal terms have even entries, because the parity of the diagonal terms are given by the Wu classes, which depend by all this whole thing over there on the normal fibration. So in general, you can perfectly well, like CP2 has a single diagonal entry, which is 1, and that's intimately connected to the fact that the normal bundle of CP2 is not trivial. First Diffie-Whitney class, or the second Diffie-Whitney class is non-trivial. So in this case, it's also this second Wu class. But in the case when k is odd, then we are if k is odd and b and nu m is fiber homotopy trivial, nice. The choice by b choice of B determines psi, I should call it P psi. Here we're in very interesting territory, named that of the Cavern invariant, or the Contryagin invariant, or the Arf invariant, many different names, but well, Cavern Arf invariant. So the choice of psi in this case, is crucial. For example, the simplest case is if M is S1 plus 1, then B, there are two choices of B. There's one which gives the Cavern invariant 0, one which gives the Cavern invariant 1. So for example, if you look at the frame, closed group of frame manifolds, that's Z2. Exactly according to whether you've got the standard framing or the exotic framing. If the framing extends over one of the S1 plus C2, you know it's boring and it has Cavern invariant 0, and it's kind of framed convolution to the empty manifold. If you take the so-called Lie framing, then you get a non-standard thing. So let me just perhaps. So this is the simplest case where the search abstraction actually that does something. It tells you which class you are in here. Let's have it over here.
I saw that example. You talked about that example in one of the
Who is he?
Patrick, when we were reading for about the Rocklin invariant.
Oh yes.
We looked at that example. It was
Absolutely. So now we come down to what was the first example, and now will be our last example. Be more careful. So here we have got a skew symmetric form. Because that's the intersection form of the torus. I can somehow see this directly. I should draw the torus. There's one circle, there's the other, there's the intersection one. Now, this is our degree one map. And there is the bundle map. So there are two choices. So B. So you could have the boring choice, the one which corresponds to the zero there, or the exciting one. So it's the same equation. But because of these two ones, you cannot, so that's T2B1 . A long time ago I talked about the surgery abstraction groups. So I'll just finish by saying that this is the simplest case. And in the general theory, so now coming back to where I started, that the surgery abstraction theory groups are groups of, so at the end of the example, so now skipping enormously forward, I'll now the wall we have all the ingredients. LNA can be expressed I did in 1980 or so, as so the walls actually goes very much earlier, 10 years earlier, 10 years to, but 5 years to work out what he was saying and 5 years to work out what I should be saying. Expressed as the coordinates groups. C psi. Exactly Q, the quadratic groups times before, with C finitely generated free model chain complexes. And 1 plus T psi naught chain equivalence. The duality here uses the like that. Now, and then if F, so in the original setup of wall, M had to be manifold and X could be a Poincare complex. But in fact, there are many advantages to this theory, I claim. And one of them is that you can have, exactly as up there, a degree 1 normal map for manifold for Poincare complexes. This is a degree 1 normal map of Poincare complexes. And then you can write down something called the quadratic signature. So this is the Umke map as defined at the end of the last lecture. And then there's a quadratic structure. And it lives in the, well, like that. The only thing to be careful of is what A is. A, if you allow yourself the university covers, is Z command of X. So this is the definition for let us call it the wall surgery abstraction. Here. And the great virtue of this formulation is that I don't have to, no need to distinguish between n even and n odd. So the original theory spent a lot of time working with the even dimensional case and forms, and the odd dimensional case, the things called automorphisms of formations, and this is as homogeneous in the dimension as manifolds are. So it's very unclear, in fact, but true, that these groups are four-periodic. So all the groups are four-periodic from the start, so it's true. And kind of a lot of the modern applications of surgery theory use some version of this. I think I'll stop at this point. Thank you very much for listening to all this ravings and ranting. Thank you.